So welcome everybody. Today, I will say a few words about the assignment, and then I have prepared some feedback quiz for you with 3 points to get. I only made one mistake. My list was printed in portrait mode, so your names are pretty small, but you all have good eyes, huh? If you have issues, just write down your name below that. I only have 4 copies today. One thing, if some of you are not registered yet in Moodle or Iml Online, then you don't get access to the assignments and everything. Please make sure that your email is somehow written down on the list. You can give it to me as well or send me a name, an email, because Julia Schmelz, she's the student assistant for this course. She can send out the assignments via email as well. She's doing that for Günther. Günther will start as a PhD in September, but he can't be registered right now. You know, there are always workarounds. For the assignment two, assignment two has to be submitted this week. No. Touch ID does not work. Whenever my finger is not dry enough. Let me have a look. So Julia and I, yesterday, we discussed all assignments, and some of you asked if we could release them right now, so you could work over the vacation days and such things. Yes, at some point we could think of it, but this year we are changing everything. So we are overworking all the assignments. In the past, these assignments, you could simply give it to ChatGPT and it would solve it for you. Here, please don't use ChatGPT alone. Try to understand what you are submitting. For the assignment 2, there is a last point here that is called entity relationship diagram. Can you see that? Yeah. I think I should share my screen here. Otherwise, you won't see that in the recording. So, entity relationship diagram, what is asked here is actually an UML diagram, because in UML, diagrams are more general. Entity relationship diagrams are meant to be used to prepare data sets, generate large databases, sorry, not data sets. And here, you should use this basic statistic class in a diagram that you draw. Hand drawing is fine. Use any graphical tool you want. I don't care. But make sure that there are at least 3 different objects. They are somehow connected. So you could think of potential experiments where you have data sets, you have multiple data sets. For each data set, you have multiple columns, and you would like to compute basic statistics per column, for instance. Just an example. Are there any questions to that? Okay, then one more thing, because we just found out, Yuri and I, that there were some issues with the last assignment. So I will present that on Friday as well, the results. I don't know why this screen is looking differently. Ah, yeah, now I know. So, there were a few almost identical submissions. These submissions get 0 points. Beware if you have identical submissions where it's obvious that you just copy and pasted it, then you get 0 points. There's no exception. And if you change some comments, and that's it, then you get 0 points. So the assignments are not difficult, but I want you to do it yourself. Another thing is we have to be more strict with the assignment name. Everything is precisely described on Moodle. It's precisely described how you should submit your files. Please follow these rules. Otherwise, Julia takes enormously long to correct your assignments, and she only has 10 hours per week. And at some point, she won't be able to correct your assignments anymore. Then you get 0 points because you did not follow the rules. So if functions are renamed or you remove return arguments or input arguments, then Julia has issues correcting your files because your function is not properly defined anymore. And then you might also have some issue with your points. At the moment, she still tries to correct everything manually, but on the long run, assignments are getting more extensive. She won't have enough time. So be careful, follow the rules. It's allowed that you add arguments. So you see my mouse pointer. If you think that a function would benefit from one more input argument, let's say some learning rate parameter or some other hyperparameter, add it, go for it. You are improving the code. That's fine, but don't remove things. Okay. I stop here because I will present it anyways on Friday, but maybe not all of you are on Friday in the exercise. Now let's see if that is working. No. Now I'm starting the quiz questions. I've prepared 3 questions. Here we go. Oh, sorry. Done already? You don't need bonus points, yeah? I see. Overloading is also okay. As long as it compiles for Julia, I can ask her. I don't. Yeah. Normally, you might add one argument because Julia did not think of this hyperparameter and you have it in your implementation. And an optional argument is always good. Yeah. I come just in time. Mm. Hmm. All right. That should do the trick. Just to show you that I'm recording the blackboard, but I'm not sure if the video quality is good enough for you to use these videos of blackboard stuff. So, all right, let's start. Which was the first question? Which statements about there is a T missing in about loss functions are correct? The L1 norm is given by the absolute value of the difference where D denotes the resulting L1 distance. That's correct. The L2 norm is given by the cosinus hyperbolicus function. No, that's wrong. The disadvantage of the L2 norm is its sensitivity to outliers. That's true. There's just an S missing. The L1 norm is not differentiable at 0. That's also correct, if you remember. And then the pseudo-Huber loss and the cosinus hyperbolicus loss functions combine the advantage of the L1 and L2 norms. So these are two examples. There are many more that try to combine these benefits. So to repeat, number 1 is correct, number 3 is correct, and number 4. Second question. Yeah, and number 5. Yeah, sorry. Second question. Which of the following equations are correct? Now I have to be careful what is written there. So the first one is wrong. You know why? It doesn't work like that, yeah? If you apply the transpose operator to these two terms here, then they would be reversed, and the transpose operator would be applied to both of them. Otherwise, the dimensions would not match. If this is completely new to you, you should have a look at some matrix calculus cookbooks, something like that. So we had A times W transpose, this term here. Now, if I apply this transpose operator to both terms, so this is a vector, this is a matrix. Can you read that? It's a bit small from that side, but I will explain it. Now, you have the vector W transpose times the matrix A transpose. This is the result. You could also think of the dimensions. Let's mock up some dimensions. Let's say A is of the dimension 10 times 20, and W, the vector, is 20 times 1. Column vector, according to our definition. Now, if I apply here the transpose operator to that one, then this dimension is 1 times 20, and A transpose is 20 times 10. So this works out. You see that? Let me check if you can read that. Well, if I would write on that blackboard, we wouldn't record it. But there are so many empty seats. If you have issues, I will only write today on these 3 blackboards. So I highly recommend to move to the center or to the left-hand side. All right. Second equation, let me check. This one looks correct. Third equation looks a bit more complicated. This one is okay. A transpose times y is also okay. Y transpose AW is okay. A transpose AW, the quadratic term. This is correct. So the third equation is correct. It's exactly the result that we will derive when we derive linear regression. Yeah, using gradient descent. And the last one should be wrong then. Yeah, here's something missing. There's also a trick how to verify that all these equations are correct or not. These are objective functions that I define here. So they will all turn into a scalar. Each individual term is a scalar. Even if there are 4 terms, the product of 4 terms, it will result in a scalar. Otherwise, something is wrong. And the last question. So this one is a bit tricky because the second one, we did not derive these results yet. We talked a little bit about matrix calculus, but not too much. We will do that in the next lectures anyways. So the last one, the solution for W given an equation A times W is given by, let me check. Who thinks that the first one is correct? Yes, and I agree here. For squared matrices, you can directly invert A, and it's totally fine. Who believes that the second one is correct? This one is wrong. We derived that result, so you remember what we did. And the last one is correct. I want to do that anyways again, so I will start with that one. So to wrap up, the first one is correct, and the last one. Now, on the slides, let me check. Yeah. There are a few things on probabilities. Come to that later. We don't need that now. So recap. The last time, remember what we did. No, I'll start with an example. This is a table with some data. In the first column, you have your y's. And then you have your features. X4, X5. And in the end, you have n rows. Now let's assume y is your target variable, something that you would like to predict. You would like to model that. For instance, This is some engine RPM value you want to control. Give them some temperature values of your complex machinery. So your goal is to build a model like that, where you have all your X values this is X, the matrix, and is of the dimension n times, in this case, 5. But let's be a bit more general. We have d dimensions. Could be 5d, yeah, in this example. Now our W vector is of which dimension? You all know it. What's the dimension of W? D. I think I heard it anyways. And then this works out. N times D times 1 resides in n times 1. So Y has the dimension of n samples, scalar. Now, last time we said we would like to compute W. And I'm now repeating that. But I put it into the context that you want to predict something. So this is your Y. And here you have X1, X2, and so on. You have D dimensions. And in the end, your goal is to predict these Y values from your inputs. If I would only have one X to make it simpler, this model here, how would this model look like in a 2D graph? I've been drawing such a nice nonlinear function. Would that be our model? Would our model represent this nonlinear function? No, it would not. Because it's a linear model, our model would actually model a straight line. But still, we start with this linear model, and throughout this course, we will turn these linear models into nonlinear models by applying some feature transformations. I will come to that also today already. So you remember, we had this X times W, and we multiplied from the left-hand side this equation with X transpose. So we had X transpose times W, the vector, is equal to X transpose X times W. And then the trick was, now this matrix is a squared matrix. Now I can invert it. And you remember, if you're not sure, always think of the dimensions. So this term here is T times N. This term here is per definition N times D. Now, the product of these two matrices is a squared matrix of the dimension T times D. Can you read that? Or do I need to push the blackboard up? It's okay. So we are multiplying now the whole equation from the left-hand side by the inverse of our squared matrix of the dimension t times t. Now I need some space. So our W vector is given by x transpose times x, the inverse of it, times x transpose times y. Correct? So this is the pseudo-inverse. You remember from the last time, this part here is called pseudo-inverse. Now this is a nice model, but it's not so powerful. How can we make that more powerful? So in our linear world, if it's two-dimensional, we had our targets, our x, we had some observations, they could be nonlinear, but our model is a linear one. Just x times w. This is our linear model. Now what if we would transform each individual sample here into a different space? These are our n samples from our data set. Now let's assume this is again our target that we would like to predict, but this is now a different space. And in this case, probably the linear, let's make it a bit more obvious that the linear model is not good. So there seems to be some linear trend, but then it really ramps up. Your problem is nonlinear, and you can't approximate it properly with a linear model. Now, let's assume that we will map each individual point here using a function. Now I'm using red again. And this function is using some sigma. Sigma is the function that we call it now. Of x times w. So you transform your model here into a different space. And your assumption is that if this function is well chosen, then suddenly all these points can be nicely represented by a linear function. This point is here. This point maps to this point, and so on. Now, if I look at this nonlinear function, I could draw something that you all know. What is that? What I'm drawing here? Is this already a neural network? So this is called a perceptron. That's a singing neuron. And this singing neuron here computes your target according to the nonlinear transformation of your inputs, x4. Here we again have x5. And for each of these x, you have some weights, W3. These are all scalars now, so therefore there's no underline. So a perceptron the sum over I is equal to 1 to 5 of xi times wi. I have to close the parentheses. So this is the output of your perceptron. Hmm? This sum is hard to use in more complex systems. How can I replace this sum using vector calculus, matrix vector calculus? So do you have any idea? In the end, it has to be a scalar, the result, R1. Do you have any idea how you would do that? Think of x. X is of the dimension n times t. W is of the dimension d. So there's something that I have to mention here. The small x is a scalar, W is a scalar. And you're computing this output here for each individual sample, for the n samples. Now this is 5-dimensional x. W is also 5-dimensional. It has to turn into a scalar. So what you can do is you can say that this prediction is given by the activation function of a vector x, which is per definition a column vector. So we transpose it, multiplied by W. Would that work? Let's find out. So we said the small x is a d-dimensional column vector. Now x transpose is 1 times d. W is per definition also a d-dimensional column vector. So what is the result? A scalar, exactly. And that's what we wanted to have, R1. So in the end, we are able to use perceptron in such a way that I have a single equation. I don't need the sum anymore. And what does it do? the sigma function transforms our original data points x into a feature space while multiplying it with w. So now I have to check if I forgot something on my cheat sheet. Ah, yeah. What is a common activation function in a perceptron? Which activation functions do you know? Exactly. Would you be able to write it down or to draw it? I have it here. It's okay. Sigma of A is given by, if I'm not using any wrong signs, no, everything is correct. 1 divided, this is a minus, by 1 plus e to the power of minus a. How does this function look like? This is now sigma of a. Here's a. What happens if a is 0? If a is 0, then e to the power of 0 0.5. Exactly. So let's say here is 1, then here is 0.5. So for a equals to 0, we are here. For very small, for large negative a values, this term here converges to 0. 1 divided by 1 equals to 1. So the sigmoid function looks like that. Sometimes there is a transformation you would like to pass at 0 through really 0. Then you shift the whole function down. That's doable. In this case, sigma prime of a is given by, what do you think? How can I push this function down? I just have to subtract 0.5. Sigma of a minus 0.5. And I could also rearrange the equation. You can do that also yourself. You will see that this is pretty easy. But this is a very common nonlinear function for perceptrons. Good. Then I need my projection. Let me check one thing. I think there must be some perceptron example on our webpage. Python perceptron example. Ah, yeah. Check if I have that already here. Mm-hmm. Why did I not create a Jupyter notebook out of that? It doesn't matter. I simply create one now. I'm not sure if this will work immediately. Functions are okay. Dot function is okay. Okay, there's a main function. Hmm? Who believes that this will compile? I'm pretty sure that we are missing some libraries. No, in this environment, everything is installed, it seems, huh? All right. Combines. I can upload this file to Moodle. But what can you see here? You see here a typical classification problem, one-dimensional classification problem, where y can be belonging to the blue class or to the green class. We denote these class labels by 0 and 1 binary values. And our model is a linear model that is just a linear equation, a linear function like this linear model here. But we are using a perceptron for that. Let me check. So we defined here a perceptron. It has a learning rate, some input dimensions, some number of samples. We have our model weights W, and we initialize them using rand n. What does that mean? Normally distributed. We come to that because today we won't come to that today. Probability theory, I will start with that next time because it doesn't make sense to match that now, to mix that with the linear regression thing. It's anyways better to focus a bit more on linear regression because assignment 3 that I will present on Friday is about linear regression. So rand n is a normal distribution. With some mean mu. Here we have again a sigma, but this is now the standard deviation. This is not the nonlinear function that we had in the perceptron, but this is the standard notation for it. So this is a normal distribution. And we typically initialize our weights with samples from such a normal distribution, because ideally we would like to start with very small weights. You don't want to assign large values to your W vector, because then you would create predictions that are super far off. So ideally you would like to start with a safe system that would predict 0 at the beginning. So you draw samples. Here you have 0. And most of the samples will be located around 0. Some will be a little bit off, because normal distributions have a property that is called long tail. Who knows what that is and why is that beneficial or an issue? You as machine learning expert, you need to be aware of that. That normal distributions are sometimes not the best. The thing is, if you look at the probability mass of such a normal distribution, it's a bit dark, I know. I can turn on the light. Okay, so otherwise we are not recording everything. So most samples are around 0, that's true. But these normal distributions, they have a very long tail. And you still have a lot of support in far off regions. And that might be a good property for some tasks, but often this is problematic. And you would prefer to use a distribution that would have less support. Like this one. One example of such a distribution is the student T distribution. Now, coming back to the perceptron example, let's have a look here to the code. Can you read that? Can I make that larger? Yes, a little bit. So the prediction itself is just a variable. Okay, then we have the derivative of the error, derivative of E. We need this derivative to compute an update law. Now there is some activation function here, and this one has to be defined. Where is it? Here. This activation function is a class that has a method called transform, and this is exactly our sigmoidal activation function here. Let's have a look. 1 divided by 1 plus of e to the power of the negative input value. Can you see that? So it's exactly our sigmoid function. So we are loading some data points here, this iris data point. Mean zero unit. What did I do here? I'm normalizing the data. And here I'm computing the training error. So for each individual sample, I store this sample in a column vector X. I have my target value Y. I have here X times W transpose, exactly what we did here. That's this product. And then I pass that product through the transformation function, our sigmoidal function, to compute the output. So this is the prediction of the perceptron. With the prediction and the true label Y, these two things, I can compute the difference, the error. And we call this the objective function. If I go to the objective function, you see what I did. Well, this is a smart way of computing the quadratic error, the L2 squared norm, actually, using vectors. So after computing the error, I'm storing the error because I want to log that, I want to print that, I want to see that it goes down, it converges to zero, ideally. I'm computing the derivative of my objective with respect to my model parameters W. And this is the derivative. We will also derive that in the class. For the moment, you have to trust me that this is the derivative of our objective with respect to the model parameters. Do you remember when we talked about gradient descent, why we are doing that? Who can give me an intuitive explanation of why are we computing here this derivative in this example? Exactly. So remember, last time when we talked about the gradient, we said, let's assume you have some objective E, you have some parameter W, and you assume that this objective has some shape. And for a particular point, let's say this one here, you try to find out what happens if you increase or decrease your W value. And to do that, you're computing here this gradient. And based on the gradient, you assign a small update to your W parameter such that the error is minimized. After this small update, so let's say this is your small update, you observe this point. You're again computing the gradient. You apply a small update, and so on. This approach is called gradient descent. And in each individual step, W t plus 1 is equal to the old W minus some learning rate times the gradient of your error E with respect to W. Actually, this is, the notation is not super correct. We don't need the nabla operator here. So it's the gradient of the objective with respect to the W parameters, dE with respect to dW. Is there any question to this iterative update scheme? Let's have a look where this is applied. We are computing the training error here, and here we are updating our weights. This is the delta W. It's another way of writing this. Can also say WT plus 1 is given by WT minus learning rate, and then you have a delta W. Here's the delta W, here's our learning rate. And we denote our learning rate here with eta, the Greek symbol. And delta W, this term, I have to define that. It's the derivative of the objective with respect to our W parameters. That's it. Just two ways of writing this iterative update rule. After applying the update, we compute the training error and we plot something, plot the error. Then there's a plot function for the input data for x0 versus y, the 2D plot. And now we can start again. The training error is printed here on top. This is iteration 0. You see that our model really is mismatching all the data points. But with the subsequent updates, it converges to a nice area where it correctly separates this two-dimensional plane. And you also see that the error goes down. Now, what happens if I choose a very large learning rate? Here, the learning rate is 0.3. What happens if I use 300 here? Let's see. That's a pity that we don't see the plots. In Visual Studio Code, you would see an updated plot always. So now it executes it. You see that actually it diverges. The sum of error is 50, regardless of the iteration. So for large learning rates, it completely diverges. And if we use a very small learning rate, then the updates, you will see that, won't have strong effect and it takes a long time to converge. Why is that not doing anything? Ah, it's busy. Okay. We have to wait. Good. We have half an hour. Let's talk about probabilities. That's all fine. All right. So in the script, you find a complete chapter about probability theory. In this chapter, I start with a discussion of two different views. I have a slide on that. Then you find definitions of random variables, probability space. We start with probability space, then we define events, random variables. Normally, I also do that in the lecture, but I will do that, I think, next week. I will start today with that. Why is that important? Well, linear models are nice, but you can't model the variance with a linear model. A probabilistic model would predict that. A probabilistic model would predict that you might have larger noise values for high temperature values compared to low temperature values. A probabilistic model can capture that. So the point is, I've just given a presentation this week to some company members and also some professors about our research. And here we say, well, in our domain, we have to process high-dimensional complex data from RGBD cameras, from tactile sensors. And in the end, we want to make predictions to control complex systems like this humanoid. The humanoid that we just bought has 43 degrees of freedom. And this is a tough problem. Everything has to be done in real time. And the biggest problem is that everything is noisy. Sensors are noisy. The actuators do not execute exactly what you send to them. Then the observation that you get or the manipulation that you perform, if you change something in the environment, you push something, you apply some force, everything is affected by noise. Then we are learning from experts' demonstrations. So experts tell our systems, they guide them, they show how to solve things. Also, these demonstrations are noisy. So everywhere is noise. And that's also depicted here in this image, where you see in autonomous driving, actually, capturing and modeling the noise is essential because you need to be aware when it's foggy, when it's rainy, when it's dark, which sensor is the best to use for autonomous driving. So very simple example. Now, there are two principled views. The first one is that everything is deterministic. This model is deterministic. This model is deterministic. If you compute that million times with the same values, you will get million times the same result. So the agent's actions uniquely determine the outcome. Chess, no randomness. Then there's the other view that everything is stochastic. So there is some randomness involved. Like if you throw a dice here, you might get different observations every time you give it a new try. Now, what are the principal assumptions and underlying important concepts for machine learning? In the deterministic world, we assume exact measurements, computation results. That's often faster and simpler. Noise is suppressed. You're not modeling it, you're suppressing it. You are eliminating the noise in your model. Your model would, after throwing away all these observations, your model would only predict dots on this line. So you're suppressing noise. So using only the last sensor value, using average of k last values, using the median of k last values, these are examples, yeah? Such systems cannot react to dynamically changing observations, environments, uncertainties. Here is again the autonomous driving example. There's another one. In the past, rule-based fuzzy logic systems were very popular. Who knows any fuzzy logic example, control example? Well, in Graz, when I studied, we also learned fuzzy logic systems, control systems. We also implemented them. And I was back then told that such fuzzy logic control systems are implemented in many systems, aircrafts, for navigation. And who knows how such a fuzzy logic system in principle works? So you could imagine that the fuzzy logic system is a rule-based system where you have some error. For instance, you want to steer towards a certain direction with your aircraft. You're off by 10 degrees. Then you apply a moderate action, correction. If you're off by 30 degrees, you apply a strong correction. And if you're off by 90 degrees, then you apply a particular behavior. So you have these rule-based systems where you don't have a single equation that explains the control law. You have a rule-based system, so you can cover multiple cases. So it's actually a very smart thing. What is the drawback of this concept, of this idea? What do you think? Think of more complex control problems, more complex systems. Why is it not so popular anymore nowadays to apply fuzzy logic for control? What would you guess? Yeah, there are nowadays different techniques. Well, yeah, but this is the main issue with the fuzzy logic system, that you have to specify these rules. And whenever you have a new sensor, you need to develop new rules. Whenever something changes, you need to develop new rules. And you can't maintain that. It does not scale. It simply explodes. That's the main drawback of fuzzy logic systems. So classical lookup tables, classical regression models, that are all deterministic systems. Now to the stochastic world. I will also finish after this slide, I promise. So here we assume that our measurements are noisy. Our computations might be noisy. So whenever you compute your best action, your control signal, it might be slightly different. Here, noise, this is the most important thing. Noise or sensor uncertainty are modeled, considering statistics like histograms, using probability distributions that will be covered in the course. And such systems, they can adapt dynamically to sensor uncertainty changes in the environment. Here are some examples: Bayesian models, Markov models, probabilistic models, inference and graphical models. And this is also the core topic of this course: probabilistic machine learning. Here's a very nice demo. Try that out yourself. It's a very nice web page. I like it a lot. You can play around here with probabilities, with chance events. Flip the coin, flip it 100 times. You see what happens. This is a fair coin. I can change the probabilities. I can flip it again. If I flip it once, you see, every time I flip it, you get a different distribution, yeah? And if you flip it very often, it will converge to the true distribution. This is a very simple example. There are way more complex examples as well. I stop here. I think this is very nice. And next time I start with the probability theory, and I do that on the blackboard, I will give you some examples. We will discuss mainly Gaussian distributions. I will introduce a distribution called beta distribution. I will tell you that there is a difference between continuous distributions and discrete distributions, and you will understand how a random variable relates to a probability density function, how you can use this probability density function as a model for machine learning. In the end, we will have a model, but the model is a distribution. All right, I stop the recording for today.